So I'm Joe Campbell. So I'm an assistant professor at Purdue University. And I'm going to give a talk today. I'm going to keep it a little bit more on the casual side, and I'm going to talk about some super recent work that I've done with my lab at Purdue, and more of like a vision and how I'm thinking about things going forward, particularly with respect to lifelong learning, as it is in the title. So specifically, I'm going to talk about agents that know what they know. The subtitle being Interpretability, Introspection for Lifelong Learning, and I'll get into what that means in a little bit. So first, I'm going to start off with a few videos. So I was at a robotics conference last week in Vienna. So I don't know if anybody online or does robotics, but it was called the ICRA, so the Conference on Robotics and Automation. And so they do this robot parade every year, and all the exhibitors and the people that bring robots for competitions will take them and they'll walk around. And I mean, in general, like as somebody that's been in robotics a long time, you see this sort of massive, I think, growth year over year and the capabilities of them. Like we see some of it here. So you have like the Unitary robots, which are just like insane capabilities now. And of course, this humanoid marathon, the in Beijing, that was like a month or two ago, where it's like now, a year ago, they were taking 12 hours to finish the race. Now they have superhuman performance under the same conditions that humans do. Uh, and on top of that, it's not even limited to embodied agents like robots, but we also have things like, Claude over here that learn to play Pokemon and and all the coding agents and everything else and OpenClaw and all these things. So the capabilities that we're seeing coming out of AI, including things like robotics, are really like astounding. But the problem is that by and large, to this point, the they're trained on a fixed set of tasks and then they're deployed, and that's it. And yes, they have some, particularly when it comes to foundation models like LLMs, there's some adaptation that you can do in context learning, but in general, the capabilities are fixed and they don't get updated until the next model release. And that's why we see LLMs, we see constant new model versions coming out to add new capabilities, right? They do not acquire these on their own. And so, but really, this is the hallmark of intelligence that we need. This is lifelong learning. So I think in agents, it's not enough to just deploy them on a fixed set of tasks and then release them into the world and that's it. Now they're frozen in time. They need to continue to learn from experience. So they need to learn from new tasks, new environments, and new collaborators. So for example, if I deploy my robot and it starts off only knowing one task, but then it encounters a new one, it should be able to learn from this new task and dynamically as it collects experience, via reinforcement learning or what have you. And same thing if we change the environment, same task, but new conditions maybe, or if they're collaborating with people, it should be able to learn from these things and grow its knowledge as it improves things. And so the argument that I'm putting forth, so this is kind of again the way I've been thinking about it in my lab and puzzling together my research with my students is I think introspection is absolutely necessary for lifelong learning. So by that, I mean agents have to be able to reason about the depth and breadth of their knowledge. So in other words, they have to know what they know. So it's kind of, I've been flying a lot lately because I was just at the conference last week, for example. And there's this sort of, comic and well-known joke out there where they're like, oh, is there a doctor on board? And like, if I'm on an airplane, like I'm a doctor, technically, right? I could stand up and like, well, I can help. I'm a doctor. What do you need? Of course, like I'm a PhD, right? I'm not a medical doctor. And so, if I were ChatGPT, if I were an LLM, do I know that distinction? Or if I go up there to the person having a medical emergency and maybe they need emergency surgery, if I'm an LLM, I'm gonna be like, stand aside. Don't worry, guys. I got this. And dig my hand in there and start trying to fiddle around to see if I can fix the problem, right? Like I don't need to do that as a person. I know I'm not a surgeon. I know I should be nowhere near any sort of medical intervention. And yet AI still does not have this capability, right? So like we know about the famous thing where they're confidently incorrect. And that's something that we need to get over. The one capability truly missing that we need intelligence is the agents have to know their own capabilities and what they can do. And so the way I'm thinking about this lifelong learning problem is really through three questions here. So one is an agent must be able to recognize its own knowledge and capabilities. So it has to know what it knows. So what do I know? Next then, if it now that it knows what it knows, next question is like, okay, so for when I encounter a new task, when I'm trying to learn from this new experience, when can I reuse what I know? Is this task similar to any of the other tasks I've encountered? Can I reuse any of this knowledge to accelerate my learning in this new task? Because otherwise, like I don't, if I already know how to do it, why would I learn how to do it again? I don't have to. I already know how to do it. So let's just bring forward that knowledge. And the third part of this is if we don't know how to do it, what do I still need to know? Like, how can I learn that most effectively? Is there any part of, like, how do I find that fine decision boundary between what I know and what I don't know? So I only learn exactly what I need to as efficiently as I possibly can. So acquire in the missing gaps in my knowledge. And so I'm going to talk about each of these three things in turn. Again, some recent areas of work where we've been pushing. And I'm going to start off with this first question. And so what do I know? So I'm going to start with like a little bit of a visual example here. So consider this little illustration of an autonomous car. This is just your car approaching a four-way intersection here. And let's assume that it's can take one of four possible actions. So it can go straight, it can turn left, it can turn right, and it can stop. And let's assume this is an agent. It's operating according to some policy. And so this policy is just a probability distribution conditioned on an observation of the environment. So, for example, if we see a red light, the probability of taking the action for stop should be very high because we want it to stop at this light. And similarly, if it's green, it should be very high probability to go forward, to go straight. And if there's people, same thing, very high probability to stop. So the actions are selected according to this probabilistic policy here. Now, the thing is, for, assuming that this policy is a deep neural network, which I think is a safe assumption these days, uh, the way that we approach a generalization of these models, we cannot possibly train it over every single unique state that we could encounter in real life, right? It's uncountable. It's impossible. And so instead, we rely on generalization claims. But the thing is, we assume that the set of states and observations that we're going to encounter when we deploy the model is drawn from the same distribution as when we train the model, right? That's the IID assumption, independent, identically distributed samples when we train our model. And so if this doesn't hold, then this means what we're seeing now, the agent has never seen before in training, right? So if we encounter something completely new now, like for example, I'm driving along my intersection and I see a cop or a tornado or somehow blue shell from Mario Kart, right? Like this is something I never saw before in training. If I look at my distribution in training, I only saw red lights, green lights, yellow lights, people, cars, stuff like this, right? These are all completely new. So my model's never seen it before, and we can't trust its outputs, right? This is something novel. We violated the IID assumption, mathematically speaking. And so the way I'm thinking about this sort of self-knowledge then is this introspection where an agent needs to know what it knows is without a distribution detection. So formally, we can just define it according to, I'm in this kind of simple case here, where g of x just represents whether a given state, a sample is in distribution or out of distribution. And then we have a simple scoring function here, s of x. So this just produces a scalar value. And this scalar value is, we compare it to a threshold tau. So if the value is greater than tau, then this indicates that the sample comes from something that looks very much like the training distribution. Therefore, it is likely the agent saw it before in training. If it is less than tau, then we assume it comes from a fundamentally different distribution and the agent would not have seen it in training. And so you can think of this as sort of classification problem in a sense. So S of x, our score function here, is approximately measuring how likely the model has seen a sample close to x during training, with the ideal case that the higher the value of the score, the more confident we are that we have seen it. And the lower the value is, the less confident we are that we have seen it. And so remember, I am assuming now that this notion of out of distribution detection is really sort of a subset of self-knowledge. Like this is sort of the first steps for an agent to understand its own capabilities. There's obviously more involved in that, but as a baby step, at least, we can have an agent look at a particular thing and say, have I seen something like this before? And that's something really important here. So now this question, what do I know? I'm converting to what have I seen during training? So a relatively straightforward transformation here. So this OOD detection problem is not a new thing. This has been around for a long time. The thing is, prior works. So if we consider a deep neural network like this, which is a standard dense feed-forward one, they mostly only compute out of distribution detection, like algorithms, whatever they be using, heuristics or thresholds or whatnot, using activations or features from the penultimate layer. So the final layer is the outputs, they grab it from the layer here. And for whatever reason, like this has been good enough so far, right? whenever people are benchmark chasing and whatnot, you're like, okay, yeah, this roughly satisfies it. We don't have to look at anything else, just the final layer of the network. But if we think about it, the final layers can discard useful evidence of distribution shift because as we progress through the network, we are basically discarding all information that is not useful for whatever objective we're training for, the downstream task, right? We're basically compressing it all away. We only have to keep what's useful over here. And we don't want to actually, when we're training for generalization, if we keep anything else, that increases the odds that we're going to capture spurious correlations, which means less generalization. So all these like regularization tricks and everything else we do are basically built with the intent of getting rid of everything that's not necessary. And so now when we only look at the final layer, guess what? We got rid of everything that's not necessary. But if we go and we can look through at a layer level here, the intermediate layers definitely capture important information. So this is a UMAP, a 2D projection of ImageNet 1K. So, I mean, it's a standard ImageNet data set, 1,000 classes and so on. And those are the gray dots. They're a little hard to see here. They'll become more visible when I move forward. And what we have here, the other color dots are basically corruptions of them, visual corruptions. So we add things like brightness, fog, motion blur, pixelation, etc. So this is a data set called ImageNet C that you can use. And these represent covariate shift. So typically, if you train a classifier in cats and dogs, and then you corrupt it with noise, the classifier is probably going to perform less well, right? Because covariate shift and corruptions. And so when we look at the final layer, or the penultimate layer, we see that the different data points are all entangled. We can't separate them at all, right? There's no way to distinguish any of these classes from each other just with this 2D UMAP projection here. And same thing if we go back a layer, still very entangled. You really can't see anything here. But now look, you step back one layer further and look what happens. Now you have super trivial separation between the OOD. Like let's assume that the corrupted data sets are OOD between the OOD ones and here, right? And we can do that even at a 2D projection level. And we step back one further at layer 4 and we still see that, right? So this is like a perfect example here that depending on what you're doing, like if you're doing OOD detection, the intermediate representations can really encode super useful things depending on what the distribution shift is or the mismatch lies. And we're not the only ones to be thinking about it in this way. So this was a paper I like last year on a Meta called the perception encoder. And they were looking at very similar things here, where, typically when you use foundation models, like vision foundation models or language models, people typically grab the embedding at the final layer of the output and then, use that as input to other models for downstream tasks or fine tune it or what have you. And what Meta did is they were looking at this and they found that actually intermediate layers sometimes perform much better for those downstream tasks. You don't want to grab the final layer. You want to grab some of the layers before it, depending on the task. And I'm not going to spend too much time going into these results, but if you roughly, this show up. If you look at, so for example, spatial tasks or language modeling tasks, so the y-axis represents their accuracy here, and the x-axis represents the layer, you can see that the peak of the accuracy is almost never at the end, right? It's somewhere before that. And so other people are seeing this too now. And so really the biggest question is, how do we use the intermediate representations? Do we just grab activations out of all the layers, slap them together in some way and try to use them? Like that's not so easy because they're super high dimensional and the information is super noisy and so on. And so what we actually did, so again, this is relatively recent work called sparse autoencoders for interpretable out of distribution detection, is we use something called sparse autoencoders, which I'll describe that in the next slide, but bear with me for now. Basically, it's a way to make sense of the activations for each layer. So let's assume that this model here, this is a vision transformer, and we can assume it's frozen. So it has a sequence of transformer blocks, right, as VIT does. And after each block, we have a sparse autoencoder, which is an autoencoder. Presumably people know what that is, but it has a sparsity constraint, which I'll discuss. And basically out of the sparse autoencoder, we get a this encoding that comes from the bottleneck layer, right? The difference is with an SAE, this encoding represents semantic information, like human interpretable information, concepts. So for example, if I feed an image of penguins into this, out of this, this SAE after transform block 1, like some of these nodes might represent the gray fur of the penguins. So like this node would only activate when an animal with an image of an animal with gray fur shows up. for example. Or for example, if the image has animals that contain wings, or and as we get further in the network, they become more global, the concepts. And so now we might have penguins and the waddle penguins because there's multiple of them and so on. And so really the sparse autoencoder gives us these sort of latent encodings with high level human interpretable concepts. And then what we can do is we can aggregate those together into an OOD scoring function. And so that S of X that we looked at earlier is essentially now a distance between the concept encodings for a given sample and then concept encodings that we saw from our training data. So for example, when you train the model, you might want to keep around the mean encoding for your data set. And then now you can basically compute for any given sample how far away we are in a concept space. But otherwise, the same thing applies. If it's greater than its threshold, it's in distribution. If it's less than threshold, it's out of distribution. So sparse autoencoders, again, those have been around for a while. I would say a few years ago, they started becoming really popular in the NLP community for interpretability. So essentially, again, it's just an autoencoder. Only the input to it is the activations out of a layer. And then at the output, also activations that you're reconstructing. And then you train this using a reconstruction loss as you do as an autoencoder. The bottleneck layer, though, traditionally in an autoencoder is going to be smaller dimensionality than your input and output. Here, not necessarily the case. It's typically actually bigger. The size of dimensionality indicates how granular your concepts will be. If it's smaller dimension, each concept necessarily has to be a little bit broader, a little bit more abstract. And so the idea, in, at least in the interpretability community, is that sparsity is a proxy for interpretability because it's information compression, right? Like we are saying basically that like, okay, take this, high dimensional activation and compress it into only a few number of active nodes. And then I can go through and look for patterns in the images of like what kinds of images activated this node. And now that's how I can derive labels and understand what sort of information has been carried. There's an added benefit for OOD detection, which is if you look at the activations, I mentioned they're high dimensional and pretty noisy. And so like if we have this sort of, ideal figure of a decision boundary between in distribution and out distribution samples, it can be very jagged and very noisy and very nonlinear. But because this information is very high level, it's conceptual and human interpretable, it smooths out this decision boundary. It's more global information, it's higher level abstracted information. And so it makes that OOD detection a bit easier to do as well. So I don't love going through tables. I threw this in here just as a matter of course. So this is so we have a bunch of data sets that we're looking at here. That's not necessarily the important part. The only thing that matters here is that this is looking at when we have label shift between the set of tasks that we trained over, and now we give samples from a new data set, and the labels between these data sets don't match. Like maybe they have unseen classes, maybe the label function is different, what have you. The only important thing that really matters is the average performance when we use this intermediate information. So the shaded row is when we're using this, is we get like rather large improvements across the board in OOD detection classic accuracy. So this is the first value is like AUROC, second value is like a FPR 95. And same thing covariate shift. So instead of changing labels, it's like the ImageNet corruptions I showed earlier, P of X. So if we add perturbations to our input noise, same thing, much improved across the board. So again, it's really kind of the big takeaway is I don't want to get into the nitty-gritty of like table values and stuff, but it's really kind of this. Using the information from the internal information from the model, the activations, always improves performance. It never hurts us. So like this is looking at it now. So this is relative performance when we use information from all the layers minus the final layer only. And these are positive values. So here we gain, 4.8 AURC. Here's 4.7, 4.6, 3.0. It's never negative. We never lose anything. So there's no reason not to use it. And in some places, we gain huge benefits out of it. And there's a little bit of an added benefit where now we can kind of, because we have labels for the SAE concepts. And so we can go back and look at each layer and see like, okay, if a sample is determined to be OOD, like where did the concept start going wrong? Like if we look at the helmet here, we get concepts that activated like, oh, it's a catalog style object, it's orange brown, glossy and curved, military ceremonial uniform. Adds up, looks consistent. if we look over here, like this, it's a flower of some sort, and it's like repeating greater lattice, no. Mesh or skill-like lattice, no. Intertwined cylindrical form, not really. You could maybe make an argument for. And like beetles and weevil-like insects, no. And same thing even down here. This is like a marble tile, and it's giving me animals and stuff. Like so you can see that it kind of lets you, and some of the samples get a bit more interesting, where it's like you can see like maybe the earlier concepts will be right, but then it starts cascading the errors, and things get wrong further in the layer. So it's really kind of a little bit of diagnostic utility here. So anyway, that is one way where I'm making an argument that I think OO detection at a bare minimum is necessary for a base level of introspection, for an agent to know what it has seen before. So now from that, again, we have the remaining two questions. When can I reuse? And it is knowledge I do know. And then what do I still need to know that's left over from that, and how can I learn it? So let's look at this next one here real quick. Been on my time. So when we do lifelong learning, and again, going back to that first figure in the talk, where I expect an agent to, as it encounters new tasks, to learn them, to be able to solve them, and not forget about old stuff, but continually add to its experience and its knowledge. The new task is rarely all new, right? Like there's usually some overlap with what we had before. So maybe you guys played cooking games like this Overcooked. And so basically what it is it's a cooperative cooking game. And so it's, shenanigans where you have these crazy different design kitchens, and you have recipes up here, and there'll be different recipes like cook a steak or cook a hamburger or a pizza or whatever, and you have a certain amount of time to do it. And the way the kitchen is structured and the time you have to cook each one, people have to work together. And you have to go get the ingredients and cook them and chop them and put them all together and deliver the dish. And so the idea is that if I know how to cook a steak over here in this kitchen environment, does it help me cook a steak over here? Like the environment's different, the kitchen layout's different, the recipes I might encounter are different. Like maybe this has more in steak, maybe this has recipes that haven't been encountered over here. But does that mean I should learn this entirely from scratch? Like surely there's some information I can carry over, right? And so the idea, let's assume that we're training this task in reinforcement learning. So let's look at like a standard RL training curve here, which maps your policy reward against the number of environment steps. So RL being, your agent is taking actions, observing the resulting reward, and then updating its policy so as to maximize rewards, right? So when you roll out the policy, your sequence of actions gives you maximum utility, maximum reward. And so let's say that if we, standard tabula rasa RL, we start trading from scratch, is something like our dashed line. If we have knowledge that we can reuse to speed things up, then I would expect it to look something like the blue line, right? So our trading curve converges a little bit faster, and maybe your reward is a little bit higher, right? However, the reason you have to be careful is because you could also reuse harmful knowledge, and that would degrade performance. Now you're going to converge slower and maybe to a lower reward. And so by a harmful knowledge, I mean things like RL is sequential decision making. So where you explore depends on your current state, and your current state depends on what you did before. So if you take bad actions, like if I'm an agent and I'm exploring my environment to try to figure out where the maximum reward is, if I have some bias in my exploration pattern and I keep walking into the corner of the room every single time, then I'm only going to be exploring this side of the room largely. And I'm not going to explore the rest of it. I bias myself over to that region. So you have to be very careful to avoid transferring bad knowledge that's going to bias the exploration to low reward regions of your state space. And so then how do we determine whether knowledge is helpful or harmful? So we can go back to out of distribution detection. So it's the same setup before, right? So your scoring function, if it's greater than tau or in distribution, I'm saying that those states are now helpful. That knowledge is helpful. And if the scoring function is less than tau, it's out of distribution, and that knowledge that we have for that state is harmful. And so this is making three assumptions here, basically. The knowledge that we are reusing comes from, also called a teacher for now. I'll give some more information on what I mean by that, but it makes the definitions a bit easier. Is that the teacher that we are transferring from performs better than random in this given state X. Because if it performs random, then we're not transferring anything anyway. It doesn't matter. the task is encoded in the observation because our scoring function is a function of x. It's only a function of state. It doesn't capture reward function or task description or anything else, right? So in order to capture behavioral properties, what you want the agent to do, that has to be as part of the observation x. And the last thing is that the teacher is trained using on-policy learning. And I'll get into why that's important in a second here. So now, just like before, this question of when can I reuse my knowledge has been transformed from when I have seen it during training. So we assume that if my agent has seen this state before, and if it performs reasonably well, better than random, then I would benefit from reusing that knowledge. And this turns into an OOD detection problem again. So again, remember that I said that out of distribution detection is really a subset of self-knowledge here. So if we think about this from the perspective of sort of a standard MDP setup, where we have our student agent policy that's learning this new task, and it's interacting with an environment, and the environment changes. So you get back your next state and your reward, standard sort of MDP loop here. Now we're injecting this additional teacher. And so this teacher, again, this doesn't have to be a different policy. This can be the same student policy, maybe just like a frozen copy of it before it started training a new task, right? Basically just represents a snapshot of what I knew at the time before I started corrupting my policy with the new learning here. And so because we're formulating this OOD detection, our first step then is to check if our current state we're in is in distribution or out of distribution. And if it is, then we transfer knowledge. We reuse our knowledge. So in this case, that transfer looks like this. So like if it's in distribution, then we transfer by basically sampling the action from my teacher policy and taking it. And if it's out of distribution, then I don't transfer. If my student policy here is a randomly initialized policy, I just sample from that. If it's starting from the teacher policy, then I will want to add a good amount of entropy. So that way I encourage random exploration and I don't get biased by walking into the corner of the wall again. So in the specific work I'm going to talk about here, we use the slightly different OOD detection than this one is sparse autoencoders. We use something in energy-based formulation from energy-based models, although in practice, it should work just fine with the SAE stuff. There's some theoretical requirements on when these generalize with the scoring function. Basically, the scoring function has to not necessarily be monotonic, but approximately so, where a higher score means it is more in distribution, right? And a lower score means it's less in distribution, or less in distribution, yeah. More OOD, I guess. And as long as your scoring function satisfies that, you can use any OOD method. But for the sake of this, I'm going to talk about energy. Yeah, we can get into this. So actually, I'll discuss this super quick. So basically, if we think about a cooking task here, and again, and if we assume that some of the task is transferable, there's some knowledge that we can bring forward, then when we're talking about the energy, so this is an energy distribution over all the states that we might encounter in a task. And remember that we're using the energy as a scoring function here. So we still have our tau, our threshold. So basically, we're trying to say that if our energy is along the x-axis, if an energy of a state is higher, is above this sort of threshold, this red line here, then this means that I've seen a state before. And so it is in distribution to me. And so roughly speaking, if we have a task and some things are OOD and some things are ID, we're going to have this sort of bimodal distribution, right? Some of the things I'll have seen before, some of the things I will not have seen before. And the goal of the OOD detection then is to find this distinction as closely as we can, and then only transfer the knowledge for these safe states that I think I've seen before. And that's basically the rough idea of it. So the specific energy formulation we use, this is just based off of like free energy from energy-based models. People have experience of that. It's basically the log sum exponentiation of the logits of the different layers here. And so the idea is that if I mentioned before, a teacher need to be trained with on-policy reinforcement learning. So that is because when you train with RL on policy, you are training the agent to visit states that yield high reward, right? At the end of the day, the agent has to choose a sequence of actions that maximize reward. That means states that yield high reward will be visited more because the agent wants to keep repeating them, right? It's the exploration exploitation trade-off, but eventually it should be exploiting here. And so as if a teacher is, the agent is more familiar with the state it is more in distribution, meaning it has seen it more. That means that state is more likely to yield high reward. And so now that's the connection. So we're basically saying higher reward states are less OOD. They are more in distribution. And remember that scoring function, it represents this. So the higher the scoring function, the more familiar it is to our agent, and the higher the reward we expect it to achieve, which means the more valuable that help is, that knowledge is to reuse. And so we have some theoretical proofs for asymptotic monoticity. I don't want to cover it all in this talk, but it is in a preprint that I can share. And so now going back to this equation, it's the same thing we looked at before. Helpful, instead of scoring function, it's just this energy score. That's it. Same thing here now. And so going back to the energy distribution here, we can kind of see some cool effects happen. One is if we assume that our agent originally know how to cook in a task where it had to make, let's say, onion soup and tomato soup. And then let's say now you give it a target task. And in the target task, also onion and tomato soup, but now it also has to make fish. So there's something new here. And so what happens is, I mentioned before the sort of bimodal energy distribution. So the source task, the energy distribution over the states is this sort of blue peak here. For the target task, we divide it up into two sections. So one for the shared, the onion and tomato soup over here, we see the energy almost match the source task, right? Because it's the same task. It should be very similar energy scores. We've seen it before. But for the new one, the fish, we can see it shifted to the left. So we have the second peak over here. So the blue and or the purple and the orange together are a bimodal distribution for the target task. But if we actually think about decomposing them between the different recipes now, we can clearly see where the energy lies. And so now our previously seen tasks are easily identifiable in distribution because again, we just have to identify our top threshold there, and that's it. And so again, if we are in distribution, we reuse our knowledge, we take our actions from our previous policy, and if not, we do something new, we explore. So I don't want to get, this looks super busy. I don't want to go through all of it. It's basically different types of cooking transfer scenarios, different room layouts, and so on. The big thing to take into account here is when you have this selective reuse based on self-knowledge, basically OOD detection, and then it improves learning performance across the board, essentially. Just like with the OOD detection, when you use internal knowledge, we see here the blue line is when you have this sort of selective transfer, like much better learning curves basically across the board. So you really get a benefit out of transferring the knowledge, which as we would expect to. And the interesting thing is if you do something simple, like I think everybody's first instinct is like, well, I'll just start with my existing policy and fine tune it online with RL, right? Much like what we do with language models and other things. But the problem is that it biases exploration so much. Like you can really kind of see it here. Like, so this is a scenario with a lot of transfer. So 2 out of 3 ingredients transfer. And fine tuning, which is the green line, it starts off with huge advantage because we're taking all the actions and we're there. But we never reach optimal. We never learn how to solve the third ingredient. Or here, if we only know one of the 3 ingredients, we always know how to solve that 1 out of 3, but I never learned to solve the missing two recipes, the missing 2 ingredients here. I get stuck in this bias exploration. The agent never learns to go for the other ingredients. And same here. Sometimes we see catastrophic forgetting be induced as well. Like you see it drop off a cliff here with performance. And anybody that's done RL for a while has seen this sort of collapse, entropy collapse typically. And so there's one last little thing about this, which is that effect of the threshold tau on learning performance. So we get this sort of interesting thing where if your threshold is too small, this means that we're basically admitting all knowledge. We're reusing everything. But that when we reuse everything, that means some of that knowledge is not going to be helpful. It's going to hurt us. And so this is the relative transfer performance. So basically, we want this to be higher. This will be better performance. Like it's relative to starting from scratch, from no transfer at all. And so when this is low, we see these values are actually less than 0. They're negative. They hurt performance, or they're very small values. But however, if the threshold is too large, then we're not reusing enough knowledge at all. If at the limit, if you move it all the way to 1, you don't transfer anything. And so you see this sort of shape where it has this arc where it peaks and it starts to drop a bit at the end here. And so really there's a region in here where you want to design a threshold such that you filter out the bad knowledge, but still issue enough helpful knowledge to be useful. Okay, so now that's sort of a way in which an agent can recognize what it knows, its own capabilities. It can selectively reuse it without being harmful when it needs to. And then the last thing is like, okay, so I'm out of distribution. My knowledge doesn't transfer over. What do I do now? So that's going back to this sort of setup. That is this case, right? So it's OOD does not transfer. So now this basically looks like this. So when you have the question, what do I need to learn? What is left? It's anything that I haven't seen during training. That is how we can formulate that. Very simple, right? So I don't agree with everything Jan LeCun says, but he did post this, I want to say a couple weeks ago. Um, yeah, 2 weeks ago. And so this was a LinkedIn post, which again is another topic of debate. But he had this nice thing here, which I like, where he says intelligence is not what you know, it's what you do when what you don't. What you do when you don't know. I mean, he didn't say this, but it's a quote from a psychology um, person, professor, I guess. And so again, he says, you can go on and read this, but that's a paraphrase of something else. But it's true, right? Like when we know how to do something, that's great. Like we can do it. It's what we do when we don't know. It's, there's so many phrases around this as well, right? Like smooth seas don't make a great captain and all this sort of stuff. And so the problem is that like, okay, so we don't know. What do we do? Do we just randomly explore? Do we do like RL from scratch? But the problem is that RL is super sample inefficient and exploration is super expensive and dangerous. So like, for example, you look at if you're doing post-training, like RL with language models, so expensive. Like how much was it? They were saying last year, OpenAI spent something like $7 billion, and like a pretty good chunk of that was on post-training with RL. Exploration, super expensive. Or, if it's robotics, if you have embodied AI, you can't simulate faster in real time. So I guess you could buy a bunch of robots and stick them in a room like Google and go have them collect experience in parallel and try to collect data that way. But still, there's only so much you can scale this. Super expensive for data collection. And also they can damage themselves, wear and tear, etc. And then if you have people in the mix, if you're doing like human robot collaboration and stuff, then this gets even more expensive and dangerous for the person. So RL in general, in its current state, I think it's way too sample inefficient to actually be a practical solution, but there are things we can do to improve it. And so one of these is intrinsic motivation. So when we don't know what to do, how do we solve it, right? Do we have external rewards? In most cases, probably not. Unless I'm a researcher sitting down designing an environment and a reward function to go with it. Usually the agent has to design its own intrinsic rewards. Like here's a task, I want to see this, and therefore I will generate this reward for myself. That sort of thing. And there's many different ways to design intrinsic rewards. There's curiosity, prediction error, learning progress, empowerment, information gain, yada, yada, yada. All sorts of different things. But at the end of the day, intrinsic reward is when an agent designs its own rewards internally and are not externally given. They're not given from a reward function. They're not given from a teacher. And so, one of the most common forms is what's called curiosity, which is a novelty seeking type of intrinsic reward. It's basically like the agent receives a bonus reward if it enters a state that it has not seen it before. That's what curiosity is. So it encourages the agent to find places it's never seen. The problem is if we're doing something like a task thing, like pick up the keys, and the keys are hanging on a key hook over here, my robot could go look in the fridge, right? That's novelty seeking. It receives a reward for that. That's stupid. The keys aren't in the fridge. What are you doing? Like you have to think about what the task is and not just have generic novelty seeking and curiosity, right? Novelty seeking is okay, but I want task relevant novelty seeking. I want it to know that the keys are very unlikely to be in the fridge and it should check in more practical places or not like looking up at the ceiling or whatever, right? And so, okay, so let's assume that we want some sort of task relevant novelty seeking then. It's like, where did this come from? How do I know what is task relevant? Like, I'm looking for some sort of concept here that can give me clues about where I want to look. And so, as typically the case these days, we can grab this information from foundation models, from LLMs and VLMs, sure, right? So, like, for example, if I have, an object, a robot doing some tabletop pick and place, I'm going to pick up the yellow triangle. And the LLM says, okay, you're looking for the yellow triangle. Sure, it can do that. And then if I have an image, I can run like a segmentation model and try to extract the yellow triangle. It can do all this stuff. But the problem is that the segmentation models are not real great right now. So VLMs still lag pretty far behind LLMs in terms of performance. And so if we look at segmentation, this is from SAM too. If we look at segmentation masks from this, they're not great. So this is it's hard to see. It's a wrist camera from a robot in a kitchen environment. That's like the knob of a handle, and this is the handle of the microwave door and stuff like that. And what we're trying to do is here we're trying to segment the knob, and here we're trying to segment the handle. And so these are the ground truth masks, what we expect them to look like. And this is what the VLM actually gave us, the SAM2 segmentation. And so you can see sometimes it completely misses it. And sometimes it gets it very wrong as well. So the VLM outputs are super noisy. The problem is when they're noisy, they bias your exploration, just like leading them into the corner, right? So if I use them directly, it harms learning in a lot of cases. So we don't really want to, if I have my VLM outputs and I have my vision encoder and it feeds into my policy and my policy chooses my action, my environment, I don't typically want to use the VLM outputs directly, either as input to my policy or as to generate rewards or whatever else. They're too noisy. They make too many errors. So in general, instead, what I would like to do is not use them directly, but use them more as like weak supervision for my agent. And so we can inject this sort of concept model here. So this is a concept embedding model. This also comes from the interpretability domain. And so I don't want to go too much into it, but essentially the way concept models work is you have your model and it encodes something uninterpretable to people. We don't know what the model's encoding, right? And so basically what we do is we take the model, break it in half, and we insert another layer in there. And then we apply some supervision such that we can we force the model to activate over semantic concepts. So we add this layer, we're like, okay, this node corresponds to this label. This node corresponds to this label. This node corresponds to this label. And then we add some training. So after the models, some post-training to force the model to activate these nodes when appropriate. So we're basically breaking the model and injecting this sort of concept layer in there so we can try to understand what's happening. It's a different approach to sparse autoencoders, but the end result is the same. We get some interpretability as to what's activating here. And the goal then is that now instead of using the VLM outputs directly, we can use the VLM outputs to influence these learned concepts in here. And essentially what's happening is we can treat these as noisy labels. And what happens when you train a model with noisy labels, that noise gets sort of aggregated away. It's just training error, which is fine. Almost all of our data sets have noisy labels and training error, yet we still train super accurate models over them. So it gets amortized away during training, essentially. And so specifically, we do a couple of interesting things with the concept embedding models. Again, I'm running low on time, so I won't get too into it. But we have like positive and negative embeddings here. We basically split our things. So like again, let's assume we're looking for the yellow triangle. The positive embedding would be like, okay, the yellow triangle is visible in my camera image. And that'll capture features related to the segmentation mask itself. We basically have a reconstruction loss in the positive embedding, such that the positive embedding will capture the information related to the target, to the task object. Negative embedding means it's not visible. And so that's going to capture features that allow the agent then to then like look around and search for the object. So this is the presence of it, and this is the absence of it. And then we combine both of these embeddings together into this concept. So this is not necessarily a weighted combination. It's actually like a gate. It's 0 or 1, which we use based off the actual like VLM target mask, at least during training. During prediction, it's our we can extract the mask that is in the positive embedding here. And then we can just use this sort of concept embedding for the RL policy. So again, I know this is a lot, but the only thing to take away from this is that instead of using the VLM output directly, we use it as weak supervision. So the model internally looks at what it knows. Like it's basically the difference between giving someone the answer and teaching somebody to come up with the answer themselves. And so now the agent uses what it knows and doesn't know about task-relevant objects to guide exploration here. So again, more graphs. I don't want to spend too much time on this. The big thing is yellow is this sort of concept-based exploration. And again, we see pretty strong improvements in most of the tasks. So this was using, I think, GPT-4. I don't know if it's 4.0 or 4, one of the earlier versions of it here. Were so the and oh, I'm sorry. So this is SAM2 for the actual segmentation model. GPT-4 was used for the task extraction and things like that, and the grounding of SAM2. And so we see, yeah, fairly strong improvements. As you'd expect, then the robot can go through and perform the tasks. So again, these are just some of the kitchen ones: opening microwave doors, flipping the doorknobs. This is Franca Kitchen, so none of these are like, super state of the art or whatnot. Actually, but in RL, more challenging than you think if you don't have dense rewards, because there's a lot of things to play around with in the kitchen. So this is one example of what this is, the reconstructed mask for the positive embedding. So it's not from the VLM. This is what we're predicting at runtime. And likewise, and this transfers to the real world. So this is just some basic block manipulation and block stacking stuff over here. So the more interesting thing to me is now we're having the agent look at itself and think about what it knows with respect to the task relevant objects. Like, have I seen this object before? If not, it's basically, again, it's curiosity, it's novelty seeking, but only with respect to task relevant things. And so if the agent doesn't know about it, but it's related to the task, we are encouraging the agent to explore in that direction, is what we're doing. So sort of like a guided breadth first search a little bit. And so this is a heat map of the exploration. So these are states that the agent is visiting during exploration when learning a task. And we can see when it's RGB only, it's all over the place. It doesn't even actually learn to solve the task. So these are heat maps collected during the early stages of training, mid stages of training, and at the end of training. And RGB never learns to solve it on its own. If we pass in RGBM, which is just a mask, it learns to solve it, but only occasionally. And you can see it starts to spread way over here, still way over here. And finally, at the end, it kind of learned to converge over here. But when you give it the concept driven exploration, right away, you can see already a ton of activity near the target point. And here now you can very clearly see the path leading directly to the target. So this is the start point, this is the end point, and same thing here. So it really kind of hones in exactly, and it's only exploring the path from the initialization to the target, right? It's not going around exploring unnecessary things. So it really speeds up the sample efficiency. So that's it. Again, these were just some recent works, and I wanted to kind of lay out some ideas here of how we can start to get towards agents that learn dynamically on their own from experience and move away a bit from this sort of idea of like, static models and deployed and frozen. Because I really think lifelong learning is going to be the future of where we're going with a lot of AI stuff. So yeah, that's it for me. I mean, as always, students and collaborators and my sponsors and everything else, like none of this work would be possible without them. So yeah, thanks. If you guys have any questions, like, let me know.